Okay, so this is the solution for the problem count good nodes in binary tree. The problem is labeled medium, however, the solution is really simple. It relies on one simple observation, which is a sort of general observation across any questions involving trees. Given binary tree, it just makes things easier for us. And we're going to talk about that very soon, but first, let's talk about the problem itself. You're given a binary tree, that's fine, and you're given the root of the binary tree. The end goal is to return an integer here. That integer is the number of good nodes in the binary tree. Okay, again, very simple. Now, how do you define good? A node x in the tree is called good if the path from root to x. So you have a root and you have this particular node. Now you obviously took some path to get to this particular node. You want to check if there are no nodes with a value greater than x in the entire path. In the path, you want to check if there are no nodes with value greater than x. Okay, now what one thing is really clear. Okay, apart from the fact that it's a binary tree and you need to do a DFS to traverse the entire thing, or maybe any other order of traversal, was one thing that's very clear. See, if you record whatever path you took and each of the every single values that path had, that would just be cumbersome and take a lot more space time. However, it says that there are no nodes with value greater than x. Somehow, the notion of the greatest value of the path comes into play. Because if in a path you can record what's the greatest up till now, then you can answer this question of with no nodes value greater than x. Why? Because if you have found the maximum possible variable in the path, let's say it's underscore max, and you can ensure that underscore max is always less than or equals to the current value x. If you can ensure that, then all of the values in the path are obviously going to be less than max. Okay. Why? Because the maximum is the maximum of all those paths. And so you just need this notion of underscore max, which records the maximum value of a particular path. Okay, let's talk about that with an example that should make things more clear. Let's start with the root node here. Now, what's the max of this path up till now? It's 3 itself. Okay, so we'll need that notion here and we'll have a recursive function. I'll explain why recursive in a second, but we'll have the current node and a notion of the maximum up till now. At the end, we'll returning a value, so we'll do that here. Recurse the node as root, and we'll start off with the root dot value. Okay. We have these 3 and 3 now as the starting of the recursion. That's fine. Okay, now let's move on with the recursion. Let's go ahead and visit the left child first, just for the sake of convenience. We'll look at left child and we'll say, hey, is this value? What's the condition here? Is this value less than or is this value, which is now x is 1, is greater than equals to the maximum value of till now? Is 1 greater than equals to 3? That's false, so we won't count this. Okay, moving on, then we have 3 again. Now we'll say, hey, is 3 greater than equals to the maximum up till now, which is 3 again? So that is true. 3 is greater than equals to 3. And we'll mark this as yellow node, which is it's counted. Okay, we'll go and backtrack and now we'll go for this side. Okay. Now we'll look at 4. Hey, is 4 greater than equals to 3? That is true. We'll mark it as a good node and we'll update the current maximum value. Okay. Now we'll go to the left node again. We'll look at 5. Is 5 greater than equals to the maximum up till now, which is 4? Yes, that is. So we'll make it a good node, count it, and then update the value 5 here. Similarly, when you go here, again, this 5 is only for this particular path. When we backtrack, we'll now just again use 4 as the value to compare with. At this point of time, and for any of the children of 5 here, the maximum value, the underscore max, will be starting from 5. But when we move above, the maximum value here was 4. And that is what is going to be passed for this child, for the right child. Now it should start to come together. So the core logic is what? Look, if we want to move left and right, we want to recurse left and right, that's fine. But we also want to count these values and say that is it a valid node or an invalid node? Yellow is valid and non-yellow is invalid. So +1 if it satisfies the condition, 0 else case. Okay, so we'll write it here. We'll say current equals to 1 if node dot value is greater than equals to the underscore max, else 0. Simple. Now we want to recurse left and right. So we'll have left here and we'll have right here. And we'll just call the recurse again with node dot left. And what is the maximum now? Each time we want to update the maximum as well. So we'll take the maximum of underscore max, the maximum up till now, and the current node. Pretty simple, right? And this is the exact same what we're going to do for the right case as well. Just edit this. What do we want to return now? We want to return current plus left plus right. So at each node, let's say it's this node. This node has 3 key pieces of information. First, is it itself a valid node or not? If it's a valid node, we'll do +1 score here or 0 in case it's not. Then we'll look at its children's, all the scores. So we're not looking at 4 anymore, but all of the children of 4 combined. We want the answer for the right one and for the left one similarly. And that is what we've done here. At the end, we'll just combine all of these 3 and return it above. The base case now is very clear again. If not node, return 0. In case you have reached a leaf node, then just return 0. It's not going to mess with any of the scores above. And that is it. Let's do a quick sanity check. Cool. We'll submit it as well. And let's talk about the space-time complexities. So in this kind of algorithm, we're just doing a traversal, which is order of n time. We have to reach at least once each and every single node in the tree. So that's order of n. The space complexity is a bit trickier. In a case, it's a perfectly balanced, it's a balanced binary tree. The space complexity is just the height of the tree. Is the height of the tree is in a balanced case log base 2 n. But there is no condition here that says it's a balanced binary tree. It's just a binary tree, which means that there is a case where it could go degenerate. There's just one node here, one node to the right, one node to the right of the right, and so on and so forth. You can have sort of these nodes going in either right or left directions. That is the degenerate case, and that will take up order of n space complexity worst case. Cool. So yeah, this submitted, this worked, and yeah, that's it for the solution of count good nodes in binary tree. If you have any feedback, suggestions, comments, let me know. Anyway, that's it. Thanks for watching.